Hello, and welcome to another Let's Study episode. This is on the Win32 API with the book Programming Windows, 5th edition, and today we'll be reading and working through Chapter 3 on Windows and Messages. In the first two chapters, the sample programs use the message box function to deliver text output to the user. The message box function creates a window. In Windows, the word window has a precise meaning. A window is a rectangular area on the screen that receives user input and displays output in the form of text and graphics. The message box function creates a window, but it is a special purpose window of limited flexibility. The message box window has a title bar with a close button, an optional icon, one or more lines of text, and up to 4 buttons. However, the icons and buttons must be chosen from a small collection that Windows provides for you. The message box function is certainly useful, but we're not going to get very far with it. We can't display graphics in a message box, and we can't add a menu to a message box. For that, we need to create our own windows, and now is the time. A window of one's own. Creating a window is as easy as calling the create window function. Well, not really. Although the function to create a window is indeed named create window, and you can find the documentation for this function at Platform SDK, User Interface Services, Windowing, Windows Reference, Windows Functions. You'll discover that the first argument to create window is something called a window class name, and that a window class is connected to something called a window procedure. Perhaps before we try calling create window, a little background information might prove helpful. An architectural overview. When programming for Windows, you're really engaged in a type of object-oriented programming. This is most evident in the object you'll be working with most in Windows. The object that gives Windows its name. The object that will soon seem to take an anthropomorphic characteristics. The object that might even show up in your dreams. The object known as the window. The most obvious windows adorning your desktop are application windows. These windows contain a title bar that shows the program's name, a menu, and perhaps a toolbar and a scroll bar. Another type of window is the dialog box, which may or may not have a title bar. Less obvious are the various push buttons, radio buttons, checkboxes, list boxes, scroll bars, and text entry fields that adorn the surfaces of dialog boxes. Each of these little visual objects is a window. More specifically, these are called child windows, or control windows, or child window controls. The user sees these windows as objects on the screen and interacts directly with them, using the keyboard or the mouse. Interestingly enough, the programmer's perspective is analogous to the user's perspective. The window receives the user input in the form of messages to the window. A window also uses messages to communicate with other windows. Getting a good feel for messages is an important part of learning how to write programs for Windows. Here's an example of Windows messages. As you know, most Windows programs have sizable application windows. That is, you can grab the Windows border with the mouse and change the window's size. Often, the program will respond to this change in size by altering the contents of its window. You might guess, and you would be correct, that Windows itself, rather than the application, is handling all the messy code involved with letting the user resize the window. Yet the application knows that the window has been resized because it can change the format of what it displays. How does the application know that the user has changed the window's size? For programmers accustomed to only conventional character mode programming, there is no mechanism for the operating system to convey information of this sort to the user. It turns out that the answer to this question is essential to understanding the architecture of Windows. When a user resizes a window, Windows sends a message to the program indicating the new window size. The program can then adjust the contents of the window to reflect the new size. Windows sends a message to a program. I hope you didn't read that statement without blinking. What on earth could it mean? We're talking about program code here, not a telegraph system. How can an operating system send a message to a program? When I say that Windows sends a message to a program, I mean that Windows calls a function within the program, a function that you write and which is an essential part of your program's code. The parameters to this function describe the particular message that is being sent by Windows and received by your program. This function in your program is known as the window procedure. You are undoubtedly accustomed to the idea of a program making calls to the operating system. This is how a program opens a disk file, for example. What you may not be accustomed to is the idea of an operating system making calls to a program. Yet, this is fundamental to Windows's architecture. Every window that a program creates has an associated window procedure. This window procedure is a function that could be either in the program itself or in a dynamic link library. Windows sends a message to a window by calling the window procedure. The window procedure does some processing based on the message and then returns control to Windows. More precisely, a window is always created based on a window class. The window class identifies the window procedure that processes messages to the window. The use of a window class allows multiple windows to be based on the same window class and hence use the same window procedure. For example, all buttons in all Windows programs are based on the same window class. This window class is associated with a window procedure located in a Windows dynamic link library that processes messages to all the button windows. In object-oriented programming, an object is a combination of code and data. A window is an object. The code is the window procedure. The data is information retained by the window procedure and information retained by Windows for each window and window class that exists in the system. A window procedure processes messages to the window. Very often, these messages inform a window of user input from the keyboard or the mouse. For example, this is how a push-button window knows that it's being clicked. Other messages tell a window when it is being resized or when the surface of the window needs to be redrawn. When a Windows program begins execution, Windows creates a message queue for the window. This message queue stores messages to all the windows a program might create. A Windows application includes a short chunk of code called the message loop to retrieve these messages from the queue and dispatch them to the appropriate window procedure. Other messages are sent directly to the window procedure without being placed in the message queue. If your eyes are beginning to glaze over with this excessively abstract description of the Windows architecture, maybe it will help to see how the window class, and the window procedure, the message queue, and the message loop, and the window messages all fit together in the context of a real program. The Hello Win program, Section 1 in the basics. Creating a window first requires registering a window class, and that requires a window procedure, and to process a Windows procedure to process messages to the window. This involves a bit of overhead that appears in almost every Windows program. The Hello Win program, shown in Figure 3-1, is a simple program showing mostly that overhead. So we have the file here, hellowin.c. We're including the header, windows.h. We are creating a function declaration, an L-result callback, window proc, and so we're having the hwind, uint, wparam, lparam parameters. And then we have the int win API win main function. Of course, we're taking in the h instance, h previous instance, the command line, and I command show. And it appears that we're storing the application name as hello win. We are creating 3 objects. I'm not sure objects, but we're creating 3 data points. A handle to our window, an hwind, a message class, data type, message, and a win class, data type, win class. And so after we have created this win class, we're going to assign some values to its parameters. And so for style, we're going to create a class style H redraw or horizontal redraw, as well as a vertical redraw in our style. And then we're going to assign our winproc function from above as the data point for our long pointer to the function winproc, data type or data member of our win class. We're going to put zeros for some of this extra stuff. We're going to assign our h instance from our main function, or our win main function. We're going to load the normal default IDE application icon and the default cursor, as well as a default white background. We're going to have no menu, and then we're going to add the class name, which is our application class name from above, which we have hello win. Then we begin in this lower section where we are going to register our class. And so we're going to check to make sure that we register it within this if statement. And so if it does not register, as written here, that it will pop up a message box saying that this program requires Windows NT, which is sort of an outdated message. Effectively, this will be you did something wrong with your window class. Effectively, I don't believe there's any computer in the world that won't register a valid Windows class as defined above if it is valid. But when you're learning how to program, you do want to continue to test this because there may be a time where you change something up here and it will not register. So we're going to use the register class function, passing in an address to the win class data data structure that we have used above and have defined its members. And so if we make it past here, that means our register has succeeded. And now we can begin to create our first window. So we have our hwind, which is our hwind data structure, which is our window, a window handle. And we're going to assign the output of this create window function, in which case we're going to pass in the window class name. So this is the same window class name that we used before, which is the same as our application name. And this is the same one that we have registered previously. So we must register before we end up creating a window. For the window caption, we can give it the text, the hello window program. For a window style, we can use the WS overlap window. This is going to be a most common window style. And then for our initial X, Y, and XY position on the screen, as well as how big the window is going to be, for our purposes here, they're just going to be using the default. So we want to class the create window underscore use default function. Well, not sure if it's a function. I think it's just an enumeration. But we're going to use that, passing that in as parameters. And since this is a non-child window, this is just its own window, we can have a null for our parent window handle. And then for our we're not using a menu in this application, so we can leave our window menu handle null. And we do need to pass in the program instance handle. And so that H instance that we got from our WinMain function, we can simply reuse it. And we'll reuse it for, I think, the last time here. And then some creation parameters that we're leaving null. So after we have applied all these parameters, we create this window, and it will succeed, most very likely. After we have created this window, it would have created in the background of sorts. And so we want to show this window. So we'll use the show window function, which we're passing it the window that we want to open. So we're passing in the window handle of the window we just created. And the iCommandShow is an int parameter in our WinMain function. And effectively, if we wanted to open our application in a minimized state, if we decided to do that, if we right-clicked on our program and open minimized, we could pass in the parameter here, iCommandShow, in our WinMain function to effectively open it however we want. So we can have it default to minimize, default to maximize, default just to open, and it will show. And so once we show the window, it'll either show minimized or show defaultly on screen. As soon as we do so, we want to begin updating our window. And so we will use the update window function. And so the update window function with the window handle is going to call our first, I think it's a window paint. So effectively it invalidates our window. So we will have a window on screen, and then when we use this update window, it will invalidate what is on that screen and will force it to redraw. And so we want to do this every time we open a new window. Well, we've created a new window, we want it to draw the first valid scene. So we will invalidate the first scene that is provided with the update window function right here. So after we have defined our window class, registered it with Windows, Windows says okay, then we create a window using the parameters that we want, assuming that works. We're not checking it here. I would add actually a check. If you're learning this whole system from the get-go, you want to check that the hwind is actually not null, and to, well, make sure that it's actually creating a window before you move on. It's going to be very obvious because most likely you've set this to be that the window will open up and you'll be able to see that window. So assuming all that worked, you're going to have a window on screen. But until it reacts, but until we do something else, it's not going to do anything. With this down here, we begin what is called the message loop. So we're going to loop forever. And while we're getting messages that are not the post quit message, or effectively until we get this exit message, which will be special, which will pass the get message false down here. But effectively, this get message function is constantly going to be looking for messages and storing them in our message data type structure every time it grabs a message. As soon as it grabs this message from the message queue of this H instance, it will translate this message, which changes some things. Not quite sure what this translate message actually does for us. Effectively, we have to do it before we use the message later with dispatch message. But with this dispatch message function, passing it the pointer to our message structure, it will send this message to our WinProc. And so we declared this WinProc, but we didn't define it because, well, we define it down here. So this is outside of our WinMain function. Effectively, this is our entire running function. So a bit of setup, extra checking, a bit of creation, and then we're just going to stay and live here until we're done. And as soon as we're done, we're going to return out of our WinMain function, and we're going to pass a parameter saying things went well, things didn't go well. Now, here's where the meat of the things are. We have our Windows procedure, as described in the book earlier. This Windows procedure is describing all of the behavior of our windows. So the window we've created, we have provided it with a class, and that class was pointing to this Windows procedure. So we have defined that this type of class of window uses this procedure, and now we define it here. So let's go over what is happening. So we're passing in the parameter of a window handle, an unsigned integer message, and a W parameter, and an L param. Effectively, these are also uints, I believe. Or actually, I think they're ints. But we'll use W param and L param for historical reasons, as well as, simply, I believe it is more useful and more straightforward to continue to use their data functions, because you will be most likely using these data types in built-in functions or helpful functions in the Windows processes that you would use. So, we're going to create a device context structure, I believe. I think this is a handle to a device context. And then a paint struct, which is a structure of paint. I think it's describing how things will be drawn. I may be wrong on that, most likely. And then we have what is a rectangle structure, which effectively stores, I believe, 4 values. Effectively a top, bottom, left, and right value, effectively describing a rectangle based on its top left and bottom right points. And so we get these messages, this uint message, and with this uint message, we're going to switch on that message. Each message that this Windows procedure gets is going to have a special form. And then we can use these messages and with this switch statement to begin to program our responses to these messages. So when we get a WM create message, this message is telling us that we have now created a window. And well, what would we like to do? For this Hello Win program, this message is going to play a sound. And so it's going to play this hellowin.wave file if it has one. But I believe that if it doesn't have this file, which I don't have this file, it's just going to play the Windows alert sound, like doo-doo-doo. And then we will return 0. Returning 0 on this would exit this dispatch message, and we'll go right back into the loop. In the case of WM Paint, which is called when we invalidate the window or when the window moves, and there's many things that can trigger a window paint message, such as a window moving in front of the window or behind it, or there's a lot that can cause the WM paint message. But if we're going to begin to paint on our window surface, we want to create this device context, which we use with the begin paint function. We pass it in our handle to our window, as well as a pointer to our paint struct. And so this will create our device context, as well as our paint structure. It will fill our paint structure with information required in order for it to function. In our first function, we'll be using the get client rect, which will get the rectangle describing the top left and the bottom right points of our window in relation to the main window on the screen, and pass that information to our rect structure. And then finally, we're going to perform this draw text function, which this function, using the device context, is going to draw this text, hello Windows 98, inside our rectangle, which is describing where our window is, so it will be drawing it in our rectangle, and it can actually only draw within our rectangle. It can't draw outside of our window. And it will draw it as a single line piece of text and centered in the screen, both centered as well as centered horizontally as well as vertically centered. And it's continued, so we're going to look at the rest of this program. So it looks like this is a picture of what our program is going to look like. But let's finish off on the program. So we have our end paint function, which will effectively tell Windows we're done painting, and we'll close out our sort of painting session and free up resources. And so we pass in our window handle as well as a pointer to our paint structure, and we return 0, so that is a full handling of our WM paint message inside our Windows procedure. In the case of closing the window, such as pressing the X button or closing it by other means, there are many other ways to cause Windows to ask for a WM destroy message to be sent. When that is sent, we want to post a quit message into our message queue, which I believe puts it to the top of the queue, and then it simply returns 0 on this. It ends. That is all the behavior that we want to do. We might want to do other behavior. So using this WM destroy, we can force the program to say save any progress before it quits. So we can effectively define how our program closes. We could have it shoot out a message, are you sure? We can have it quietly shut down. We can have it run to the minimize tray and not actually close. So this is where you would define stuff like that. And for all those for that switch statement shown here, all we've decided on switching on for this message is the WM create and the WM paint, as well as the WM destroy messages. Now, for all other messages, we would fall through this, we wouldn't fall through, we would skip this switch statement effectively, and we would come down to here, where we can return simply the default window procedure. So we don't need to define a lot. We can actually leave most things to default. So your minimize, your maximize, your actually, we do actually have to describe our WM destroy in the post quit message. That's the one we have to do. I would have assumed that that would be a default thing, but it's not. But effectively, our default window procedure is quite powerful and it does a lot for us. We don't have to program much more than this. It performs the entire function and be able to move it around, be able to resize it, and do everything without needing us, without needing any additional more programming. Windows has done most of that for us with the default Windows procedure. So, this program that we just read through creates a normal application window, as shown in Figure 3-2, and displays Hello Windows 98 in the center of that window. If you have a soundboard installed, which it's 2026 now, imagine everyone does, you'll also hear me saying the same thing if you had the Windows file as well, which I don't think I have. Actually, well, that's a lie. Because I do have it. I got the disc. I haven't broken the seal yet on it, but I got the disc. So I do have the Windows file. It's probably on that disc. Okay. A couple of warnings. If you use Microsoft Visual C++ to create a new project for this program, you would need to make an addition for the object libraries and linker usage. Okay, so trying to translate that into today's necessities of what you need to do. Effectively, when you're using Microsoft Visual C++, or what I should rather say, Microsoft Visual Studio, you do want to create a Windows desktop application, and a blank one at that. And that's going to change your sort of your default from your Windows console application projects. So effectively, the only thing you're trying to change is the subsystem. Because normally when you create a program for C++ or C, the subsystem is going to be the console subsystem. So the program is going to be expecting to interface with the console, and it will include only the necessary libraries in order to do that function. But for Windows programming, you're going to want to have a few other libraries, as well as changing your subsystem from console to, I believe it's called, Windows. And I believe that's actually all you need to do to actually run this program specifically. Just changing your subsystem to Windows will effectively work that. Okay. So I didn't read it, but it's effectively outdated. It's not going to apply. Okie dokie. Thinking globally. Most of HelloWin.c is overhead found in virtually every Windows program. Now, I will restate that. Everything you're going to find in this program is very much going to be in every single program using a window. You're going to have all this, guaranteed. You're going to have a Windows class. You're going to be defining its parameters. You're going to be registering it. You're going to eventually create that window. You're going to open it and show it, and then you're going to loop for messages. You might do stuff in between, or before, or even after, but You're going to be doing this at some point in time. Nobody really memorizes all the syntax to write this overhead. Generally, Windows... I will say this. Nobody really memorizes all the syntax to write this overhead. I have written so many of these programs that I believe I have like an 80% success rate with being able to write a functional outputting, getting a window on the screen, doing something very simple like drawing text on it by just pure memory. No lookups, nothing. But that's more of a sickness than a brag. The fact is, if you write a few hundred programs and you specifically do it by scratch every time, you end up memorizing a lot. Generally, Windows programmers begin a new program by copying an existing program and making appropriate changes to it. You're free to use the programs on the companion CD-ROM in this manner. Yay, I have that. I mentioned above that Hello Win displays the text string in the center of the window. That's not precisely true. The text is actually displayed in the center of the program's client area, which in figure 3-2 is the large white area within the title bar and the sizing border. This distinction will be important to us. The client area is that area of the window in which a program is free to draw. Such when I said that you can't draw outside of it, I was right. And deliver visual output to the user. So I will say this. We're trying to print, and it's saying it here, displayed in the center of the program's client area, but I'll say this. This function we use... never mind. I thought this was get hwinrect, in which case it would give the Windows rectangle. And I thought that it was using the get hwinrect function, in which case it wouldn't actually be technically in the center. It would be slightly higher because we're including the title bar in the hwinrect, because we'll be dealing with this specific top and bottom, well, bottom down here, versus starting up here, which we're getting the client rectangle, which we draw in the center. I was trying to get the author. That's how you know, that's how I know that I'm reading a little more intently, is that I'm looking for mess-ups in the author's writings. And I find it very enjoyable when I do find up a mess-up. Or, well, I look for one, I identify one, and then I, well, do what I just did, which I clarify that, no, the author actually did do the correct thing. But it's at least a method that I have to tell that, oh, I'm actually reading is where I'm looking for. I'm finding these gotcha encounters effectively. Very low percentage of the time do I ever find a mistake. This distinction will be important to us. The client area is that... When you think about it, this program has an amazing amount of functionality in its 80-odd lines of code. You can grab the title bar with the mouse and move the window around the screen. You can grab the sizing borders and resize the window. When the window changes size, the program automatically repositions the text string in the center of its client area. You can click the maximize button and zoom Hello Win to fill the screen. You can click the minimize button and clear it from the screen. You can invoke all these options from the system menu, the small icon at the far left of the title bar. You can also close the window to terminate the program by selecting the close option from the system menu by clicking the close button in the far right of the title bar, or by double-clicking the system menu icon. We'll be examining this program in detail for much of the remainder of the chapter. First, however, let's take a more global look. HelloWin.c has a WinMain function. like the sample programs in the first two chapters, but it also has a second function named WinProc. This is the window procedure. In conversation among Windows programmers, it's called the WinProc. Notice that there's no code in HelloWin.c that calls WinProc. However, there is reference to WinProc in WinMain, which is why the function is declared near the top of the program. So the reason why we have to make this declaration of our WinProc above is because we end up using it down here. So we have to declare it first, and we could declare and define it up here, so bringing this all together up here, but we can, it's more customary to just declare it and then define it later. The Windows function calls. HelloWin makes calls to no fewer than 18 Windows functions. In the order they occur, these functions with a brief description are load icon, which loads an icon for use by a program, our load cursor, which loads a mouse cursor for use by a program. We have getStock object, which obtains a graphic object, in this case a brush used for painting the Windows background. We use the white brush for a white background. We use the register class function, which registers a window class for the program's window. We use the message box function, which displays a message box. I believe this only happens if we fail to register a class in HelloWin.c. We have our create window function, which creates a window based on a window class, which we define in Windows C. We're going to use the show window, which shows the window on the screen. We have update window, which directs the window to paint itself. In other words, it creates the WM paint message, sends it to the message queue, and then that message queue gets handled by the window procedure, and the window procedure switches on that message and proceeds to use its bit of code underneath the WM paint message. We have the get message, which obtains a message from the message queue, so it pulls a message if there is a message. We have translate message, which translates some keyboard messages. So that's sort of what some of the handling is happening with that. I said I didn't know what it does. Well, now we learned a little bit more, so it might be doing some extra stuff about keyboard messages. I believe some of that metadata or some of that extra data might be, I think what it is like if you're pressing multiple keys at once, it is sort of, when we translate this message, this like press down message is also going to look for some other information as well, such as if you had control down, if you had a function key down, if you had shift down, a couple other stuff. And then we have the dispatch message function, which sends a message to a window procedure. So when we dispatch that message after we translate it, it'll go straight to a window procedure and it will perform the functions that it'll perform the behavior that we defined. In the play sound function, it'll simply play a sound file. In the begin paint function, it'll initiate the beginning of a Windows painting session, I'll call it. We have the get client rect, which obtains the dimensions of the Windows client area. So the top left of the client area to the bottom right of the client area in number of pixels. And it will store it in a rectangle structure. And then we have the draw text function, which displays a text string. So it will print a string of text given parameters. We then have the end paint function, which will end a Windows painting session. And finally, we have the post quit message, which inserts a quit message into the message queue, which will return false whenever our get message function hits this post quit message. This quit message will make our get message return false, which will break us out of our message loop. And then we have our def window proc, which performs a default processing of messages, in which case it's just simply very useful, so we don't have to reprogram a lot of behavior. So these functions are described in the platform SDK documentation, and they are declared in various header files, mostly in winuser.h. Uppercase identifiers. You'll notice the use of quite a few uppercase identifiers in HelloWin.c. These identifiers are defined in the window header files. Several of these identifiers contain a 2-letter or 3-letter prefix, followed by an underscore. So we have CS for a class struct, or class style, I should say. We have CW for create window. We have DT for, actually I don't remember DT. MB for message button or message box, I think. WM for Windows message. WS for Windows style. So you get to start learning this over time, and you'll get a memory for it. But these are, I very much appreciate it. I very much like it. And they're simply numerical constants, so they're just all of these are just enumerations. They're not complex data structures. They're just enumerations. Or, well, they're numerical constants. Well, I mean, I guess an enumeration is a numerical constant as well as an additional little extra bits. The prefix indicates a general category to which the constant belongs, as indicated in this table. So let's see if I was right about these things. So CS, class style, I was right about that. CW, create window, I was correct about that. DT, I didn't know it was, but it was draw text function. Okay. So DT for center, the single line, and vertical centering, as well as, well, they didn't put it in here. I guess they ran out of space, but there was a horizontal center, I think. Nope, it's right there. My bad. Well, it's not horizontal center, but yep. Sorry. Not sure if you even got that. Okay. And then we have these prefix and constants. So these prefixes, the IDI is for the ID number of an icon, and IDC is an ID number for a cursor. We have MB for message box options. We have SND for sound option. We have WM for Windows message. I was right about that. And we have WS for Windows style. I was right about that. You almost never need to remember numeric constants when programming for Windows. Virtually every numeric constant has an identifier defined in the header files. It's very quick and easy, and they're very organized in chunks of areas in the header files to get to these areas. So effectively, you look at one, you peek definition. I believe the function is F9, but you can right-click it after highlighting it, peek definition, and it'll send you right to the header file, right to where it is in the header file, and show you well, the area surrounding it, as well as where it is directly on the line where it's defined. You can look a little bit above, a little bit below, but you'll be right on the money with the rest of the other options and other defined constants as well. So we got some new data types. Some other identifiers used in HelloWin.c are new data types, also defined in the Windows header files, either using typedef or hashtag defined statements. This was originally done to ease the transition of Windows programs from the original 16-bit system to future operating systems that would be based on 32-bit technology. This didn't quite work as smoothly and transparently as everyone thought at the time, but the concept was fundamentally sound. Sometimes these new data types are just convenient abbreviations. For example, the uint data type used for the second parameter in WinProc is simply an unsigned int, which in Windows 98 is a 32-bit value. The PSTR data type used for the third parameter to WinMain is a pointer to a non-wide character string. That is, it's a character pointer. Others are less obvious. For example, the third and fourth parameters in WinProc, as defined as wparam and lparam respectively, the origin of these names requires a bit of history. When Windows was a 16-bit system, the third parameter in WinProc was defined as a word, which was a 16-bit unsigned short integer, and the fourth parameter was defined as a long, which was a 32-bit signed long integer. That's the reason for the W and the L. So word and long prefixes on the word parameter. In the 32-bit versions of Windows, however, wparam is defined as a uint and lparam is defined as a long, which is still the C-long data type. So both parameters to the window procedure are 32-bit values. So I was right, I think, with thinking that they were both the same size, but I was incorrect in knowing that I assumed that the lparam and wparam were both integers now, but it looks like the wparam is a uint and the lparam is an int. So right now, I believe the only difference is being unsigned and signed integers. This may be a little confusing because the word data type is still defined as a 16-bit unsigned short integer in the Windows 98. So the W prefix to param creates somewhat of a misnomer. The WinProc function returns a value of type lresult. That's simply defined as a long, okay? The WinMain function, I just learned that. The WinMain function is given a type of Win API, as is every Windows function call defined in the header files. And the WinProc function is given a type of callback. Both these identifiers are defined as __std call, which refers to a special calling sequence for function calls that occur between Windows itself and your application. HelloWin also uses 4 data structures, which I'll discuss later in this chapter, defined in the Windows header files. These data structures are shown in the table beginning in the next page. Okay. So we have MSG, mighty good soup. MSG is our message structure. We have our Wind class, our window class structure. We have our paint struct, which is our paint structure. We have our rect, which is our rectangle structure. The first 2 data structures are used in WinMain to define 2 structures named MSG and WinClass. The second 2 are used in WinProc to define 2 structures, namely PS and rect. Getting a handle on handles. Finally, there are 3 uppercase identifiers for various types of handles. We have the identifier hinstance, which means a handle to an instance for this program itself. We have the identifier hwind, HWND, which is a handle to a window. And we have HDC, which is a handle to a device context. So I was correct on that. Good on my memory. Handles are used quite frequently in Windows. Before the chapter is over, you will also encounter H-icon, a handle to an icon, H-cursor, a handle to a mouse cursor, and H-brush, a handle to a graphics brush. A handle is simply a number, usually 32 bits in size, that refers to an object being a thing with both memory and function. The handles in Windows are similar to file handles used in conventional C or MS-DOS programming. A program almost always obtains a handle by calling a Windows function. The program uses the handle in other Windows functions to refer to the object. The actual value of the handle is unimportant to your program, but the Windows module that gives your program the handle knows how to use it to reference the object. And we'll talk about Hungarian notation. You might also notice that some of the variables in HelloWin.c have a peculiar looking names. One example is SZ command line passed as a parameter to WinMain. Many Windows programmers use a variable naming convention known as Hungarian notation in honor of the legendary Microsoft programmer Charles Simonyi. Very simply, the variable name begins with a lowercase letter or letters that denote the data type of the variable. For example, SZ prefix in SC command line stands for string terminated by 0. The H prefix in H instance and H previous instance stands for handle. The I prefix in I command show stands for integer. The last two parameters to WinProc also use Hungarian notation, although as I explained before, wparam should more properly be named UIParam for unsigned integer, but because these two parameters are defined using the data types wparam and lparam, I've chosen to retain their traditional names. When naming structure variables, you can use the structure name or an abbreviation of the structure name in lowercase, either as a prefix to the variable name or as the entire variable name. For example, in the WinMain function in HelloWin.c, the message variable is a structure of the message type. WinClass is a structure of the WinClass type in the WinProc function. PS is of paint structure, and rect is a rect structure. Hungarian notation helps you avoid errors in your code before they turn into bugs. Because the name of a variable describes both the use of a variable and its data type, you are much less likely to make a coding error involving mismatched data types. The variable name prefixes I'll generally be using in this book are shown in the following table. So we have a C for a character or wide character or tchar data type. We have the BY for our byte, our unsigned char, N for short, I for int, X and Y used as int for X or Y coordinate. We have CX or CY used as X or Y in length. C stands for count of pixels. We have B or F for bowl, F for flag. We have W for word, which is an unsigned short. We have an L for a long. We have a DW for a D word, which is an unsigned long. We have FN for function. We have S for string. SZ for a string terminated by the 0 or the null character. We have H for handle, and we have P for pointer. Registering the window class. A window is always created based on a window class. The window class identifies the window procedure that processes messages to the window. More than one window can be created based on a single window class. For example, all button windows, including push buttons, check buttons, and radio buttons, are created based on the same window class. The window class defines the window procedure and some other characteristics of the windows that are created based on that class. When you create a window, you define additional characteristics of that window that are unique to that window. Before you create an application window, you must register a window class by calling register class function. This function requires a single parameter, which is a pointer to a structure of the type Win class. This structure includes two fields that are pointers to character strings, so that structure is defined two different ways in the winuser.h header file. First, there's the ASCII version, Win class A, shown here. Notice some uses of Hungarian notation here. The LPFN prefix means long pointer to a function. Recall that in Win32 API, there is no distinction between long pointers and near pointers. This is a remnant of 16-bit Windows. The CB prefix stands for count of bytes and is often used. Okay, I did not know that. That's good to know now. Because I was always wondering what that CB meant. And is often used for a variable that denotes a byte size. The H prefix is a handle, and the HBR prefix means a handle to a brush. The LPSZ is a prefix for a long pointer to a string terminated with a 0. The Unicode version of the structure is defined like so. We have a Win class W structure, with effectively the same as above, with the addition of, I'm looking over it, nothing but our long pointers to our strings is now wide strings. The only difference, I don't know why I bothered. The only difference is that the last two fields are just defined as pointers to constant wide character strings rather than pointers to constant ASCII character strings. If I just read the next sentence, it would have told me what to find. Well, at least I'm doing what the book is doing as well. We're technically on the same page. After winuser.h defines the window class A and the window class W structures, and pointers to the structures, the header file defines Win class and pointers to Win class. Some include for backward compatibility, based on the definition of the Unicode identifier. When I show subsequent structures in this book, I'll show the functionally equivalent definition of the structure, which is for Win class is this. So we have a struct down here. Okay, so we have Win class A, Win class W, and now we have this Win class. I'll go easy on the various pointer definitions. There's no reason for you to clutter up your code with variable names beginning with LP and NP. In WinMain, you define a structure of type Win class, generally like this. Win class, win class. You then initialize the 10 fields of the structure and call register class. The two most important fields in the win class structure are the second and the last. The second field, LPFN winproc, is the address of a window procedure used for all windows based on this class. In HelloWin.c, the window procedure is winproc. The last field is the text name of the window class. This can be whatever you want. In programs that create only one window, the window class name is commonly set to the name of the program. The other fields describe some characteristics of the window, as described below. Let's take a look at each of the window class structure in order. The statement winClass.style equals our class style of H redraw or horizontal redraw, and our HOV redraw, which is our vertical redraw, combines, and we use this vertical line, which combines, I think it's the OR statement, which is our OR bitwise C operator, combines two 32-bit class style identifiers with a C bitwise OR operator. Woo! Bam! Nailed it. Didn't even read it. The Windows WinUser.h header file defines a whole collection of identifiers with the CS prefix. So it's like if you went to the Windows thing, you would see all these definitions right down here. Alrighty. I actually don't know many of these. I think I've only used vertical and HR redraw. I'm curious what no close means. The window that can't be closed. That's important. It's a fun way to make some malware. Identifiers defined in this way are called bit flags because each identifier sets a single bit in a composition value. Only a few of these class styles are commonly used. The two identifiers used in HelloWin indicate that all windows created based on this class are to be completely repainted whenever the horizontal window size, with HRedraw, or the vertical window size, VRedraw, changes. If you resize HelloWin's window, you'll see that the text string is redrawn to be the new center of the window. These two identifiers ensure that this happens. We'll see shortly how the window procedure is noted of this change in window size. The second field of winClass structure is initialized by the statement winClass.lpfn winproc equals winproc. This sets the window procedure for this window class to winproc, which is the second function in HelloWin.c. This window procedure will process all messages to all windows created based on this window class. In C, when you use a function name in a statement like this, you're really referring to a pointer to a function. The next two fields are used to reserve some extra space in the class structure and the window structure that window maintains internally. A program can use this extra space for its own purposes. HelloWin does not use these feature, so 0 is specified. Otherwise, as the Hungarian notation indicates, the field would be set to a count of bytes. I'll use the CB wind extra field in the checker 3 programs shown in chapter 7. Ooh! Is there a checkers program? I wanted to write some checkers and chess programs. Ooh, we got something to look ahead for. Okay, checker program. I'm excited. The next field is simply the instance handle of the program, which is one of the parameters to WinMain. We have our Win class .hInstance to be set to our H instance. The statement WinClass.hIcon is set to our load icon, the output of the load icon function, looking for the IDI application icon, which sets the icon for all windows created based on this Windows class. The icon is a small bitmap fixture that represents the program to the user. When the program is running, the icon appears in the Windows taskbar and at the left side of the program Windows title bar. Later in this book, you'll learn how to create customized icons for your Windows programs. Right now, we'll take an easy approach and use a predefined icon. To obtain a handle to a predefined icon, you can call loadIcon with the function argument set to null. When you're loading your own customized icons that are stored in your programs.exe file on disk, this argument will be set to hInstance, the instance handle of the program. The second argument identifies the icon for the predefined icons. This argument is an identifier beginning with the prefix IDI, ID for icon, defined in WinUser.h. The IDI application icon is simply a little picture of a window. The loadIcon function returns a handle to this icon. We don't really care about the actual value of the handle, it's simply used to set the value of the hIcon field. This field is defined in the Win class structure to be of type hIcon, which stands for handle to an icon. The statement WinClass.hCursor equals loadCursor, or null, well, taking the parameters of null and IDC arrow, is similar to the previous statement. The loadCursor function loads a predefined mouse cursor known as IDC arrow and returns a handle to the cursor. This handle is assigned to the hCursor field of the Win class structure. When the mouse cursor appears over the client area of a window that is created based on this class, the cursor becomes a small arrow. The next field specifies the background color of the client area of windows created based on this class. The HBR prefix of the HBR background field name stands for handle to a brush. A brush is a graphics term that refers to a colored pattern of pixels used to fill an area. Windows has several standard or stock brushes. The getStockObject call, shown here, returns a handle to a white brush. WinClass.hbrBackground equals getStockObject white brush. So as we're getting lost in all this, I know it's a lot of reading. But effectively, what it did is, what we're here for, is that this is talking about registering the window class, but these things that we're interacting with are these bitwise bit flags. So you see it's CS's and these IDIs and these IDCs and these white brush. These are all bit flags defined somewhere in the Windows header files. And we're using them, and these are several cases where we're using them. So I don't think the book did it's self-evident about what we're looking at, but I don't think it did a great job of explaining that these are some of the use cases of this, where you might see this happening. This means that the background of the client area of the window will be solid white, which is a common choice. The next field specifies the window class menu. Hello Win has no application menu, so the field is set to null. WinClass.long pointer for string terminated with 0, menu name is null. Finally, the class must be given a name. For a small program, this can be simply the name of the program, which is the hello win string stored in the sc app name variable. In the win class, okay, we just have that happening there. This string is composed of either ASCII characters or Unicode characters, depending on whether the Unicode identifier has been defined. When all 10 fields of the structure have been initialized, HelloWin registers the window class by calling register class. The only argument to the function is a pointer to the window class structure. Actually, there's a register class A function that takes a pointer to the window class A structure, and a register class W function which takes a pointer to the win class W structure. Which function the program uses to register the window class determines whether messages sent to the window will contain ASCII text or Unicode text. Now here's a problem. If you ever compiled a program with the Unicode identifier defined, your program will call register class W. That's fine. If you're running the program on Microsoft Windows NT, which I don't think is possible this day and age, but if you're running the window program on Windows 98, the register class W function is not really implemented. There's an entry point for the function, but it just returns a 0 for the function call, indicating an error. This is a good opportunity for the Unicode program running under Windows 98 to inform the user of the problem and terminate. Here's the way most of the programs in this book will handle the register class function call. So this is what we saw earlier, and this is what I said is practically impossible in today's day and age. The the message box W function works properly because it is one of the few Unicode functions implemented in Windows 98. This code fragment assumes, of course, that register class is not failing for some other reason, such as a null window proc field in the win class structure. The getLastError function helps you determine, okay, so this is important, the getLastError function helps you determine the cause of the error in cases like this. GetLastError is a general purpose function, so I'm going to star this. Is a general purpose function in Windows to get extended error information when a function call fails. The documentation of the various functions will indicate whether you can use GetLastError to obtain this information. In the case of calling register class W in Windows 98, GetLastError returns 120. You can look in WinError.h to see that the value 120 corresponds to the identifier error call not implemented. You can also look up the error in the platform SDK, window-based services, debugging error handling, error codes, system errors, and numerical order. Some Windows programmers like to check the return value of every function call for errors. This certainly makes some sense, and here's why. I'm sure you're familiar with the rule that you always check for an error when you're allocating memory. Well, many Windows functions need to allocate some memory. For example, register class needs to allocate memory to store information about the window class. So you should be checking the function regardless. On the other hand, if register class fails because it can't allocate the memory it needs, Windows has probably already ground to a halt. I do a minimum of error checking in the sample programs in this book. This is not because I don't think error checking is a good idea, but because it would distract from what the programs are supposed to illustrate. Finally, a historical note, in some sample Windows programs, you might see the following code in WinMain. If not an H previous instance, will win class style is set to horizontal redraw and vertical redraw. Interesting. This comes under the category of old habits die hard. In 16-bit versions of Windows, If you started up a new instance of a program that is already running, the previous instance parameter of the WinMain would be the instance handle of the previous instance. To save memory, 2 or more instances were allowed to share the same window class. Thus, the window class was registered only if the previous instance was null, indicating that no other instances of the program were running. In 32-bit versions of Windows, previous instance is always null. This code will still work properly, but it's not necessary to check previous instance. So effectively what that's just saying is that if we went all the way to our previous instance parameter being passed in our WinMain, it's always going to be null in today's world. But you still could use it, as defined here. Creating the window. The window class defines general characteristics of a window, thus allowing the same window class to be used for creating many different windows. When you go ahead and create a window by calling create window, you specify more detailed information about the window. Programmers new to Windows are sometimes confused about the distinction between the window class and the window, and why all the characteristics of a window can't be specified in one shot. Actually, dividing the information in this way is quite convenient. For example, all push-button windows are created based on the same window class. The window procedure associated with this window class is located inside Windows itself, and it is responsible for processing keyboard and mouse input to the push button and defining the button's visual appearance on the screen. All push buttons work the same way in this respect, but not all push buttons are the same. They almost certainly have different sizes, different locations on the screen, and different text strings. These latter characteristics are part of the window definition rather than the window class definition. So we sort of have a separation between a window class definitions and a window, our create window function, so our window definitions. And so we can set one for like this is everything, and these are specifics. That's what I'm getting from this. While the information passed to the register class function is specified in the data structure, the information passed to the create window function is specified as separate arguments to the function. Here's the create window call in hello-in.c, complete with comments identifying the fields. So we have our create window function, and we're getting our window class name, our window caption, our window style, our initial X position, our Y position on screen, and our X and Y, which is our pixel size, and then our parent window handle, our menu handle, and our instance handle, as well as any additional creation parameters. At this point, I won't bother to mention that there are actually a create window A function and a create window W function, which treat the first two parameters of the functions as ASCII or Unicode respectively. The argument marked window class name is SCAppName, which contains the string HelloWin, the name of the window class the program just registered. This is how the window we're creating is associated with a window class. The window created by this program is a normal overlapped window. It will have a title bar, a system menu button to the left of the title bar, a thick window sizing border, and minimize, maximize, and close buttons at the top and the right of the title bar. That's a standard style for Windows, and it has the name WS overlapped window, which appears as the window style parameter in create window. If you look in winuser.h, you'll find that this style is a common combination of the several bit flags. We have overlapped, caption, system menu, thick frame, minimize box, and maximize box. The window caption in the text that will appear in the title window. The window caption is the text that will appear in the title bar of the window. The arguments marked initial X position and initial Y position specify the initial position of the upper left corner of the window relative to the upper left corner of the screen. By using the identifier CW underscore use default for these parameters, we are indicating that we want Windows to use the default position for an overlap window. So it's defined as, well, this big bit by default. By default, Windows positions successively newly created windows at a stepped horizontal and vertical offsets from the upper left corner of the display. Similarly, the initial X size and initial Y size arguments specify the initial width and height of the window. The CW use default identifier again indicates that we want Windows to use a default size for the window. The argument marked parent window handle is set to null when creating a top-level window, such as an application window. Normally, when a parent-child relationship exists between two windows, the child window always appears on the surface of its parent. An application window appears on the surface of the desktop window, but you don't need to find out the desktop window's handle to call create window. The window menu handle is also set to null because the window has no menu. Well, this window doesn't have any menu. The program instance handle is set to the instance handle passed to the program as a parameter of the WinMain function. Finally, a creation parameters, so I'm curious about this. A creation parameters pointer is set to null. You could use this parameter to point to some data that you might want later, you might want to reference in your program. Okay, so it's a pointer to some data. Alright, interesting. I wonder what you would use that for. I guess you could point it to like a bin file, like a compressed file for like a video game or something. I'm not quite sure. But, well, you could use it. It's just available. Which, more options available, power to us. The create window call returns a handle to the created window. This handle is saved in the variable hwind, which is defined to be of type hwind, handle to a window. Every window in Windows has a handle. Your program uses the handle to refer to the window. Many Windows functions require hwind as an argument, so that Windows knows which window the function applies to. If a program creates many windows, each has a different handle. The handle to a window is one of the most important handles that a Windows program handles. Now, displaying the window. After the create window call returns, the window has been created internally in Windows. What this means, basically, is that Windows has allocated a block of memory to hold all the information about the window you have specified in the create window call, plus some other information, all of which Windows can find later based on the window handle. However, the window does not yet appear on the video display. Two more calls are needed. The first is show window with the window handle and the I command show parameter. The first argument is the handle to the window just created by create window. The second argument is the I command show value passed as a parameter to WinMain. This determines how the window is to be initially displayed on the screen, whether it's normal, minimized, or maximized. The user probably selected a preference when adding the program to the start menu. The value you receive from WinMain to pass to show window is SW_show normal, show-normal. I think it's show normal, no dash. all caps. If the window is displayed normally, SW show maximized. If the window is to be maximized, and SW show min no active if the window is just to be displayed in the taskbar. The show window function puts the window on display. If the second argument to show window is SW show normal, the client area of the window is erased with the background brush specified in the window class. In this case, I imagine it's the white brush. The function call update window wind, let's see if I was right about this, then causes the client area to be painted. Okay, well, correct. It accomplished this by sending the window procedure, that is the winproc function in a hello Windows C, the WN paint message. Woohoo! I was correct. We will soon examine how the winproc deals with this message. Now I said a bit more, so I was correct in everything that I was just saying, but I spoke more. I said it invalidated the window area, so that may be different. Or I think the invalidation is simply a idea, and I'm just accomplishing that idea. Okay, now we have the message loop. After the update window call, the window is fully visible on the video display. The program must now make itself ready to read keyboard and mouse input from the user. Windows maintains a message queue for each Windows program currently running under Windows. When an input event occurs, Windows translates the event into a message that it places in the program's message queue. A program retrieves these messages from the message queue by executing a block of code known as the message loop. Okay, so we have the while get message loop. Where we both translate and then dispatch these messages that we get from this function get message, and we loop forever until we get a quit message. The message variable is a structure of type MSG, which is defined in the winuser.h header file like this. So we have an MSG, and so it contains a handle to a window, a uint parameter for a message, a W parameter, an L parameter, a D word for time, and a point PT. The point data type is yet another structure defined in windef.h header file like this. So we have two longs. The get message call that begins the message loop receives a message from the message queue, get message. This call passes to Windows a pointer to an MSG structure named message. The second, third, and fourth arguments are set to null, or 0 to indicate that the program wants all messages for all windows created by the program. Windows fills in the fields of the message structure with the next message from the message queue. The fields of the structure are, okay, so we have hwind, the handle to the window which the message is directed to. In the Hello Win program, this is the same as the hwin value returned from the create window, because that's the only window in the program that it has. The only window that this program has, the Hello Win.c program has. We have message. The message identifier. This is a number that identifies the message. For each message, there is a corresponding identifier defined in the Windows header files, most of them in winuser.h, that begins with the identifier WM. For instance, if you position the mouse pointer over the Hello Win's client area and then press the left mouse button, Windows will put a message in the message queue with a message field equal to WM underscore left button down, which is of the value of I don't even know how to say that. 0x0201. I think that's an octal number. Okay, we have W param, which is a 32-bit message parameter the meaning and value of which depends on the particular message. And then we have lparam, another 32-bit message parameter dependent on the message. And time, the time the message was placed in the message queue. Okay, this is useful. I didn't even know that this was available. And then we have pt, the mouse coordinates at the time the message was placed in the message queue. Okay, so this is useful. How did I not know about that? I have to explore that later. If the message field of the message retrieved from the message queue is anything except the WM quit, which is equal to the octal 12 value, get message returns a non-zero value. A WM quit message causes get message to return 0, or, well, false. The statement translate message passes the message structure back to Windows for some keyboard translation. I'll discuss this more in Chapter 6. The statement dispatch message again passes the message structure back to Windows. Windows then sends the message to the appropriate window procedure for processing. What this means is that Windows calls the window procedure. In Hello Win, the window procedure is winproc. After winproc processes the message, it returns control to Windows, which is still servicing the dispatch message call. When Windows returns to Hello Win following the dispatch message call, the message loop continues with the next get message call. The window procedure. All that I have described so far is just overhead. The window class has been registered, the window has been created, the window has been displayed on the screen, and the window has entered a message loop to retrieve messages from the message queue. The real action occurs in the Windows procedure. The window procedure determines what the window displays in its client area and how the window responds to user input. In Hello Win, the window procedure is the function named winproc. A window procedure can have any name, as long as it doesn't conflict with some other name, of course. A Windows program can contain more than one window procedure. A window procedure is always associated with a particular window class that you register by calling register class. The create window function creates a window based on a particular window class. More than one window can be created based on the same window class. A window procedure is always defined like this, as an lresult callback with a function name and the parameters of hwin, uint, wram, lparam. The 4 parameters to the Windows procedure are identical to the first 4 fields of the message structure. The first parameter is hwin, the handle to the window receiving the message. This is the same handle returned from the create window function. For a program like Hello Win, which creates only one window, this is the only window handle the program knows about. If a program creates multiple windows based on the same window class and hence the same window procedure, hwin identifies the particular window receiving the message. The second parameter is the same as the message field in the message structure. It's a number that identifies the message. The last 2 parameters are 32-bit message parameters that provide more information about the message. What these parameters contain is specific to each type of message. Sometimes a message parameter is 2 16-bit values stuck together, and sometimes a message parameter is a pointer to a text string or to a data structure. Programs generally don't call Windows procedures directly. The window procedure is almost always called from Windows itself. A program can indirectly call its own Windows procedure by calling a function named sendMessage, which we will examine in later chapters. Then we have processing the messages. Every message that a window procedure receives is identified by a number, which is the message parameter to the window procedure. The Windows header file, winuser.h, defines identifiers beginning with the prefix WM for each type of message. Generally, Windows programmers use a switch and a case construction to determine what message the window procedure is receiving and how to process it accordingly. When a window procedure processes a message, it should return 0 from the window procedure. All messages that a window procedure chooses not to process must be passed to a Windows function named defWindowProc. The value returned from defWindowProc must be returned from the window procedure. In Hello Win, WinProc chooses to process only 3 messages: the WMCreate, WMPaint, and WMDestroy. The window procedure is structured like this. We switch on the iMessage, and we have these case statements: WMCreate, WMPaint, WMDestroy, and we have what we have here, and once we're finished processing those messages, we're returning 0. And if we switched on an iMessage that is not a WMCreate, paint, or destroy, we want to return the default window proc. It is important to call defWindowProc for default processing of all messages that your Windows procedure does not process. Otherwise, behavior regarded as normal, such as being able to terminate the program, will not work. Yeah, see, this is what I was talking about. Actually, it still won't close the message. What happens is when you close it, it'll destroy the window, but you'll loop in your message loop forever, because there was no post-quit message. When default window proc processes a WM destroy message, it doesn't post a quit message by default. So that might end up having it's something I ran into a couple times when I was writing programs. Is I would close the application and it would continue to run in the debug menu, and I'm very confused. Well, that's the problem that I was running into, was my post-quit message was never being called because I was relying on the default window proc to handle my WM destroy message, which I thought it would, but it obviously did not handle it in the way I expected it to. Playing a sound file. I'm not sure if I even want to read this. That's okay. I read it. It might become useful. The very first message that a window procedure receives, the first that Hello Win's WinProc chooses to process, is WMCreate. WinProc receives this message while Windows is processing the create window function in WinMain. That is, when Hello Win calls create window, Windows does what it has to do, and in the process, Windows calls the WinProc with the first argument set to the window handle and the second argument set to WMCreate, the value 1. WinProc processes the WMCreate message and returns control back to Windows. Windows can then return to Hello Win from the create window call to continue further progress in WinMain. Often, a window procedure performs one-time window initialization during WMCreate processing. Hello Win chooses to process this message by playing a waveform sound file named hellowin.wave. It does this using the simple play sound function, which is described in the Platform SDK, Graphics and Multimedia Services, Multimedia Audio, Waveform Audio, and Documented Waveform Audio, and documented in the Platform SDK, Graphics and Multimedia Services, and Multimedia Reference and Multimedia Functions. The first argument to place sound is the name of a waveform file. It can also be a sound alias name defined in the sound section of the control panel or a program resource. I wonder what sounds are available beforehand. Might be interesting. I doubt there's actually that many. The second argument is used only if the sound file is a resource. The third argument specifies a couple of options. In this case, I've indicated that the first argument is a file name and that the sound is to be played asynchronously. That is, the play sound function call is to return the sound as soon as the sound file starts playing without waiting for it to complete. That way the program can continue with its initialization. So this is interesting. So I have a problem. I created a Morse code program that uses the beep function from the Windows header files. And that beep function produces a very harsh start and end. So it sort of starts very harshly and ends very harshly, and it ends up making this popping noise coming in and out as it sort of activates the speakers at full throttle and deactivates them as well at full throttle. Perhaps if I wrote a simple beep function similar to this beep function that is built into Windows, using this instead to run asynchronously, I can play a wave file which is smoother. One that starts slow at the normal position and gradually raises up very rapidly but smoother than the harsh popping noise beep function that is built into Windows. So this was, and it did turn out to be useful. I believe I shall use this in the future to write my next Morse code program so that it doesn't have those harsh popping noises as it translates text to Morse. And, transmits a message. The second argument is waiting for it to complete. That way the program can continue with its initialization. WinProc concludes WM create processing by returning 0 from the window procedure. I think it's really funny because I think I tried this where if you printed it, if you played the sound file, the window would pop up way sooner than the sound file would play. This is interesting. I was seriously even thinking about adding a sleep for the sound to catch up to play as soon as the window would come up. The WM paint message. The second message that WinProc processes is WM paint. This message is extremely important in Windows programming. It informs a program when part or all of a Windows client area is invalid and must be updated. Okay, I wasn't wrong. Woohoo! Which means that it must be redrawn or painted. Now, how does a client area become invalid? When the window is first created, the entire client area is invalid because the program has not yet drawn anything on the window. The first WM paint message, which normally occurs when the program calls update window in WinMain, directs the window procedure to draw something on the client area. When you resize Hello Win's window, the client area becomes invalid. You'll recall that the style field of Hello Win's Win class structure was set to the flags of CSH redraw and CS vertical redraw. This directs Windows to invalidate the whole window when the size changes. The window procedure then receives a WM paint message. When you minimize Hello Win and then restore the window again to its previous size, the Windows does not save the contents of the client area. Under a graphical environment, this would be too much data to retain. Instead, Windows invalidates the window and the window procedure receives a WM paint message and itself restores the contents of the window. When you move windows around the screen so that they overlap, Windows does not save the area of the window covered by another window. When that area of the window is later uncovered, it is flagged as invalid. The Windows procedure receives a WM Paint message to repaint the contents of the window. WM Paint processing always begins with the call to begin paint, with our HDC equaling the return of our function begin paint with our handle and our pointer to our paint structure, not pointer, our address of our paint structure, and ends with the call to end paint, with the end paint function, the window handle, and the paint structure. In both cases, the first argument is a handle to the program's window, and the second argument is to a pointer to a structure of type paintStruct. The paintStruct structure contains some information that a Windows procedure can use for painting the client area. I'll discuss the fields of this structure in the next chapter. For now, we'll just use it in the begin paint and end paint functions. During the begin paint call, Windows erases the background of the client area if it hasn't been erased already. It erases the background using the brush specified in the HBR background field of the Win class structure used to register the Win class. In the case of Hello Win, this is the stock white brush, which means that Windows erases the background of the window by coloring it white. The begin paint call validates the entire client area and returns a handle to a device context. A device context refers to a physical output device such as a video display and its device driver. You need the device context. This is interesting. A device context refers to the physical output device such as your video display and its device driver. You need the device context handle to display text and graphics in the client area of the window. Using the device context handle returned from begin paint, you cannot draw outside the client area even if you try. End paint releases the device context handle so that it is no longer valid. If a window procedure does not process the WM Paint message, which is very rare, they must be passed to the def window proc. The default window proc simply calls begin paint and end paint in succession so that the client area is validated. Okay, so we have to do that in order to get this validation corrected. After WinProc begin paint, it calls get client rect. The get client rect. Gosh, my throat is getting torn to shreds reading this much. Well, reading aloud this much. Get client rect of our hwind and our rectangle. The first argument is the handle to the program's window. It needs a T. The second argument is a pointer to a rectangle struct of type rect. This structure has 4 long fields named left, top, right, and bottom. The getClientRect function sets these 4 fields to the dimensions of the client area of the window. The left and top fields are always set to 0. Thus, the right and bottom fields represent the width and height of the client area in pixels. WinProc doesn't do anything with this rect structure except pass a pointer to it as the 4th argument of the draw text function. Draw text, as the name implies, draws text. Because this function draws something, the first argument is a handle to the device context returned from begin paint. The second argument is to the text to draw, and the third argument is set to -1 to indicate that the text is string terminated with a 0 character. The last argument to draw text is a series of bit flags defined in winuser.h. Although draw text seems to be a GDI function because it displays output, it's actually considered part of the user module because it is fairly high-level drawing function. The function is documented in the Platform SDK, Graphics and Multimedia Services, GDI, and Fonts and Text. The flags indicated that the text should be displayed as a single line, centered horizontally and vertically within the rectangle specified by the 4th argument. This function call thus causes the string hello Windows 98 to be displayed centered in the client area. Whenever the client area becomes invalid, as it does, When you change the size of the window, WinProc receives a new WM Paint message. WinProc obtains the updated window size by calling getClientRect and again displays the text in the next center of the window. The WM Destroy message. The WM Destroy message is another important message. This message indicates that Windows is in the process of destroying a window based on a command from the user. The message is a result of the user clicking on the Close button or selecting Close from the program's system menu. Later in this chapter, I'll discuss more in detail how the WM Destroy message gets generated. Hello Win responds to the WM Destroy message in the standard way by calling PostQuit message 0. This function inserts a WM quit message in the program's message queue. I mentioned earlier that getMessage returns non-zero for any message other than WM quit and that it retrieves from the message queue. When getMessage retrieves a wquit message, getMessage returns 0. This causes WinMain to drop out of the message loop. The program then executes the following statement. We return the message W parameter. The W parameter of the structure of the value passed to the PostQuit message function, generally 0. The return statement exits from WinMain and terminates the program. So we have the Windows programming hurdles. Don't call me, don't call you. Queued and non-queued messages. Oh, it's the end. Oh, we're so close. Okay, we can do this. We can do this. Come on, Froat. What is it? Voice box. We can do it. The Windows programming hurdles. Even with my explanation of Hello Win, the structure and workings of the program are probably still quite mysterious. In a short C program written for a character mode environment, the entire program might be contained in the main function. In Hello Win, WinMain contains only one program overhead necessary to register the window class, create the window, and retrieve the dispatch messages from the message queue. All the real action of the program occurs in the window procedure. In Hello Win, this action is not much. WinProc simply plays a sound file and displays a text string in its window. But in later chapters, you'll find that almost everything a window program does is in responses to messages to a window procedure. This is one of the major conceptual hurdles you must leap to begin writing Windows procedures, Windows programs. Now, don't call me, I'll call you. Programmers are well acquainted with the idea of calling on the operating system to do something. For example, C programmers use the fopen function to open a file. The fopen function is implemented with a call to the operating system to open a file. No problem. But with Windows, it's different. Although Windows has a couple thousand function calls, Windows also makes calls to your program, specifically to the window procedure we have called in WinProc. The window procedure is associated with a window class that the program registers by calling register class. A window that is created based on this window class uses this window procedure for processing all messages to the window. Windows sends a message to the window by calling the window procedure. Windows calls WinProc when a window is first created. Windows calls WinProc when the window is eventually destroyed. Windows calls WinProc when the window has been resized or moved or minimized. Windows calls WinProc when a user clicks on the window with the mouse. Windows calls WinProc when characters are typed from the keyboard. Windows calls WinProc when an item has been selected from a menu. Windows calls WinProc when a scroll bar is manipulated or clicked with the mouse. Windows calls WinProc to tell you when it must repaint its client area. All these calls to WinProc are in the form of messages. In most Windows programs, the bulk of the program is dedicated to handling these messages. The messages that Windows can send to a program are generally identified with names that begin with the letters WM and are defined in the WinUser.h header file. Actually, the idea of a routine within a program that is called from outside the program is not unheard of in character mode programming. The signal function in C can trap a Control-C break or other interrupts from the operating system. Old programs written for MS-DOS often trapped hardware interrupts. But in Windows, this concept is extended to cover everything. Everything that happens to a window is relayed to the window procedure in the form of a message. The window procedure then responds to this message in some way or pauses the message to the default window proc for default processing. The wparam and lparam parameters to the window procedure are not used in Hello Win except as parameters to the default window proc. These parameters give the window procedure additional information about the message. The meaning of the parameters is message dependent. Let's look at an example. Whenever the client area of a window changes in size, Windows calls that window's window procedure. The hwin parameter to the window procedure is the handle of the window changing in size. Remember that one window procedure could be handling messages for multiple windows that were created based on the same window class. The hwin parameter lets that's a really cool idea. The hwin parameter lets the window procedure know which window is receiving this message. The message parameter is wm size. The wparam parameter for wm size message is the value size restored, size minimize, size maximize, size max show, or size max hide, defined in the WinUser.h header file as numbers from 0 to 4. That is, the wparam parameter indicates whether the window is being changed to a non-minimized or non-maximized size, being minimized, being maximized, or being hidden. The L parameter contains the new size of the window. The new width, a 16-bit value, and the new height, a 16-bit value, are stuck together in the 32-bit L param. The windef.h header file defines some handy macros that help you extract those two values from L param. We'll do this in the next chapter. So new width, 16-bit value. So 16 bits can get us how many values? How many pixels? I want to know what's the theoretical limit of at least this function in describing the width of a screen. I wonder if we're ever going to get that screen big enough to actually run into those limits. Sometimes messages generate other messages as a result of the default window proc. As a result of the default window proc processing. For example, suppose you run Hello Win and you eventually click the close button. Or suppose you select close from the system menu using either the keyboard or the mouse. The default window procedure processes this keyboard or mouse input. When it detects that you have selected the close option, it sends a window message system command message to the window procedure. The WinProc passes this message to default WinProc, and the default WinProc responds by sending a WM close message to the window procedure. The WinProc again passes this message to the default window proc. Default window proc responds with the WM close message by calling the destroy window. Destroy window causes Windows to send a WM destroy message to the Windows procedure. The WinProc finally responds to this message by calling post quit message to put a WM quit message in the message queue. The messenger causes the message loop, the win main to terminate and the program to end. So a very complicated string of back and forths when you click the close from the system menu with the mouse or keyboard. Almost there. 2 pages. Queued and non-queued messages. I've talked about Windows sending messages to a window, which means that Windows calls the window procedure. But a Windows program also has a message loop that retrieves messages from a message queue by calling getMessage, and dispatches these messages to the window procedure by calling dispatchMessage. So, does a Windows program pool for messages, much like a character mode program pooling for keyboard input, and then route these messages to some location? Or does it receive messages directly from outside the program? Well, both. Messages can either be queued or non-queued. The queued messages are those that are placed in the program's message queue by Windows. In the program's message loop, the messages are retrieved and dispatched to the Windows procedure. The non-queued messages are the results of calls by Windows directly to the Windows procedure. It is said that queued messages are posted to a message queue, and that non-queued messages are sent to the window procedure. In any case, the window procedure gets all the messages, both queued and non-queued, for the window. The window procedure is message central for the window. The queued messages are primarily those that result from user input in the form of keystrokes, such as the WM key down and WM key up messages. Characters that result from keystrokes, WM car, mouse movement, WM mouse move, and mouse button clicks, WM L button down. Queued messages also include the timer message, WM timer, the repaint message, WM paint, and the quit message. The non-queued messages are everything else. Non-queued messages often result from calling certain Windows functions. For example, when WinMain calls create window, Windows creates the window and in the process sends the window procedure a WM create message. When WinMain calls show window, Windows sends the window process, window procedure, WM size, and WM show window messages. When WinMain calls update window, Windows sends the window procedure a WM paint message. Queued messages, signaling keyboard, or mouse input can also result in non-queued messages. For example, when you select a menu item with the keyboard or mouse, the keyboard or mouse message is queued, but the eventual WM command message indicating that a menu item has been selected is non-queued. This process is obviously complex, but fortunately, most of the complexity is Windows' problem rather than our programs. From the perspective of the Windows procedure, these messages come through in an orderly and synchronized manner. The window procedure can do something with these messages or ignore them. When I say that messages come through in an orderly and synchronous manner, I mean first that messages are not like hardware interrupts. While processing one message in a window procedure, the process will not be suddenly interrupted by another message. Although Windows programs can have multiple threads of execution, each thread's message queue handles messages for only the window whose window procedures are executed in that thread. In other words, the message loop and the window procedure do not run concurrently. When a message loop retrieves a message from its message queue and calls dispatch message to send the message off to the window procedure, dispatch message does not return until the window procedure has a return control back to Windows. However, the window procedure could call a function that sends the window procedure another message, in which case the window procedure must finish processing the second message before the function can call returns, at which time the window procedure proceeds with the original message. For example, when the window procedure calls update window, Windows calls the window procedure with the WM paint message. When the window procedure finishes processing the WM paint message,
The update window call will return controls back to the window procedure. This means that the window procedures must be reentrant. What does that mean? Reentrant. Reentrant. In most cases, this doesn't cause problems, but you should be aware of it. For example, suppose you set a static variable in the window procedure while processing a message that you call a Windows function. Upon return from that function, can you be assured that the variable is still the same? Not necessarily. Not if the particular Windows function you called generated another message and the window procedure changes the variable when processing that second message. This is one of the reasons why certain forms of compiler optimization must be turned off when compiling Windows programs. Okay, so that's important. What ones? In many cases, the window procedure must retain information it obtains in one message and use it while processing another message. This information must be saved in variables defined as static in the window procedure or saved in global variables. Of course, you'll get a much better feel for all of this in later chapters as the window procedures are expanded to process more messages. And we're almost there. Get in and out fast. Windows 98 and Windows NT are preemptive multitasking environments. This means that as one program is doing a lengthy job, Windows can allow the user to switch control to another program. This is a good thing, and it is one advantage of the current versions of Windows over the older 16-bit versions. However, because of the way Windows is structured, this preemptive multitasking does not always work the way you might like. For instance, suppose your program spends a minute or two processing a particular message. Yes, the user can switch to another program, but the user cannot do anything with your program. The user cannot move your program window, resize it, minimize it, close it, nothing. That's because your window procedure is busy doing a lengthy job. Oh, it may not seem like the window procedure performs its own moving and sizing operation, but it does. That's part of the job of the default window procedure, which must be considered as part of your Windows procedure. If your program needs to perform a lengthy jobs while processing particular messages, there are ways to do so politely, and I'll discuss in Chapter 20. Even with preemptive multitasking, it's not a good idea to leave your window sitting inert on the screen. It annoys users. It annoys users just as much as bugs, non-standard behavior, and incomplete help files. Give the user a break and return quickly from all messages. That's the get in, get out fast things. So that concludes Chapter 3 on... Oh my god, did we read a lot? Oh, where's the start? Okay, there it is. Woo! How many pages? 29 pages. That concludes Chapter 3, Windows and Messages. Most likely the most important chapter out of this entire book on programming Windows, 5th edition on the Win32 API. Thank you for watching. I am going to go to sleep now. Thank you.